I'm Richard Epworth. Just to briefly introduce myself, I joined a little later than Peter Selway. My first exposure to optical communication was at Manchester University, where in 1965 my colleague and I had the idea to build a free space optical communication system using LEDs and pin diodes. And in '66 I was fortunate to join the lab's STL at a very fortuitous time. So, my lords, ladies and gentlemen, and Charles, we're here today to celebrate the award of the Nobel Prize in Physics to Charles Kao. Forgive me for calling him Charles Kao because we all used to know him as Charlie. Those of you who are here this morning heard a story of great excitement and glamour, an invention in search of a purpose. Everybody's heard about lasers. Now, this afternoon is about a much less well-known invention, yet one whose purpose was clear from the very start: communication. This technology revolution has been hidden, both physically, as it lies underground and under the oceans, but also in terms of public ignorance. Earlier this week, I Googled Charles Kao and knighthood, and this is what came up. So we Brits certainly know how to make a fuss of our heroes. However, it probably suits the man who we're here to honour today, because Sir Charles, or Charlie as we knew him, has always been modest despite all the accolades that have been bestowed on him. For some, optical fibre communications may now seem obvious or even inevitable. However, I was there, and I acutely remember the derision poured on the idea by so many people. To appreciate the true significance of this fibre revolution, we must explore what came before and what we might have been committed to if the fibre revolution hadn't happened, and if Charles hadn't been so persistent too. So fires have been used to communicate simple but important messages for thousands of years. And the heliograph was enabled by the development of flat optical surfaces, and it was solar powered, so it was more energy efficient and environmentally friendly than fire. Alexander Graham Bell applied the idea to telephony when he invented the photophone. This was an optical telephone in which sunlight was reflected off a voice-modulated diaphragm. The modulated light was detected using a light-sensitive cell. Later, he wrote that the photophone was his greatest ever invention, even greater than the telephone. And he even wanted to name his second daughter Photophone, or Photophony, or whatever. Despite the possibilities of optics, for 1.5 centuries, copper conductors became the dominant means of terrestrial communication. The ability to communicate over the hills, out of sight, and in all weather was a huge advantage. Pairs of wires suspended provide low loss at low frequencies, and they were ideal for low-speed signals. But when many signals are multiplexed onto one conductor, such as these coaxial cables, a fundamental problem arises. The attenuation increases with frequency, so the range is dramatically reduced. Meanwhile, the development of radar during World War II had provided a wealth of understanding and skill in microwave technology, and these were soon applied to the development of long-haul microwave waveguide. Here is such a piece of waveguide. It's a hollow pipe made with a helical coil of copper wire inside, supported on a lossy structure of carbon fibre and glass fibre, and it's all held together with copious amounts of resin. It's quite heavy, and it's pretty solid. The basic idea was very good, in that the microwave energy was confined in the lossless central region, as the conjurers usually show you. And the carrier frequency offered lots of information bandwidth. The theoretical predictions of the transmission loss were confirmed by experiments, proving far superior to that achieved with coaxial cable for the same bandwidth, the same information capacity. Huge programs were established to develop the technology in all the world's great labs, including Standard Telecommunications Laboratories in Harlow. One single 10-foot section took 12 machine hours to make and used a lot of raw material. And it's important to bear in mind that this is what we would have had if fibre hadn't been developed. Now, can you imagine that going under the oceans? Can you imagine that to the home? There is possibly use for that. So just how practical were these? So the waveguides were very rigid and could only tolerate very gentle bends of a 1,000-foot radius. So the plan was to lay them beside motorways. Fortunately, STL discovered many of the problems early and completely abandoned the program in 1964, transferring key staff to the favoured optical program. Other labs had less foresight. The invention of the laser provided a powerful and highly directed source of optical power, even brighter than the sun. Unlike the sun, however, lasers exhibit temporal coherence. However, for optical communication, this property was largely ignored for many years. It was the laser's high brightness that made it so attractive. Some of us had built optical links communicating through free space using light-emitting diodes as the source. And though the range could be greatly increased using lasers, serious problems of beam stability and weather dependence were revealed, making them impractical for telecoms. Now, Standard Telecommunications Laboratories was a remarkable place. It attracted many bright scientists and engineers, all keen to share ideas with each other. Alec Reeves's optical communications group, pursued several different approaches to free space and guided optical communication. Meanwhile, a young Charles Kao had joined STC Woolwich and then moved to STL Harlow in 1960. Initially, he worked on the design of components for long-haul microwave systems, until 1963, when he joined the optical communications team, now under Tony Karbowiak. The first optical guide ideas researched at Harlow were the optical pipeline and the confocal lens system. The optical pipeline consisted of a 1-inch diameter steel pipe with a silvered inner surface. Now, we all know that metallic reflecting surfaces are lossy, so one would expect multiple reflections to severely attenuate the signal. However, the theory suggested that at shallow angles of incidence, it would have a loss of only 2.5 dBs per mile. The reality, however, was very different. Mode conversion at the joints caused the loss to be more than 200 dBs per mile. And that wasn't all. The system only worked twice a day, and then only briefly when the rate of change of ambient temperature fell to 0. A screen was constructed to shield it from daylight, but it was still a failure. And I hardly dare mention that the minimum bend radius was half a mile. In practice, there wasn't much light at the end of that tunnel. Next, the confocal lens system. This consisted of a sequence of lenses spaced apart by their focal length, 180 feet in our trial, each lens successively re-imaging the beam. But the same problems of minimum bend radius and thermal stability re-emerged. Neither of these systems controlled the direction of the light sufficiently. So next, they tried a radical change in approach, guide the light with a dielectric. The microwave experience of Charles and his team suggested that a dielectric guide would need to be single-moded to overcome pulse distortion associated with a wide range of mode velocities, and so to maximize the information capacity. Initially, it seemed very unlikely that the loss of the dielectric material could be reduced sufficiently. So structures were investigated where the light was guided using a dielectric, yet where most of the power propagated outside it. Bare glass fibres 1/10 of a micron diameter were not the answer. They were so light that they simply floated away in the air. Next, there was some serious work on thin film planar waveguide. At least this enabled the dielectric guide to be supported, and it was able to bend well in one axis. In 1964, Tony Karbowiak left for a university post in Australia, and Charles took over as project leader and stopped further work on planar guides. bare glass fibres had been used as light pipes for some time, and more recently, the idea of cladding a dense core with a much less dense cladding had led to the first practical optical fibres. They quickly found use for endoscopes and illuminators, but their useful length was limited to a few meters by the loss of the glass. I made this 20-meter fibre bundle with the best available fibre in 1967, and it had a loss of 24 dBs. Whatever, putting white light in, you get nice green light out. And these fibres were in no use at all for long-distance trunk communications. By 1964, a dielectric clad fibre looked most promising to Charles, though many others remained sceptical, believing the loss could never be reduced sufficiently. He proposed the use of a single lowest order mode, enabling the guide to carry a large bandwidth, but was concerned about the ability of such a guide to handle bends, as he had previously observed strong wavelength selective loss in the thin film waveguides. George Hockham was another bright microwave engineer who transferred from the long-haul microwave project, and he now applied his microwave insights to the understanding of the effect of mechanical tolerances and bends in dielectric fibres. There were serious concerns about the practical waveguide with such small dimensions, and the absorption and scattering losses of these early fibres was so high that they couldn't measure these other effects. So George constructed X-band microwave representations of dielectric fibres using finned rods with periodic diameter variations and measured their loss. The first quasi-single-mode fibres were made and experimented with, and here you see images of the fibre end with different launch conditions. Charles and his team now spent the next 2 years ruthlessly hunting down each of the fundamental limits, picking them off one by one until they proved to themselves that the fibre was viable. During this time, Charles' wife Gwen, a programmer, wrote much of the modelling software. Charles was doggedly persistent, never losing faith in the vision. And there were tales of threats to cut his funding and Charles driving on regardless. It all culminated in a truly historic paper, finally published in July 1966, and you should all now have a copy, hopefully. And I encourage you to explore that at your leisure, because it is a remarkably comprehensive paper for a new idea, and it addresses all the significant objections. With the publication of the paper, Charles became an evangelist for fibre. Instead of patenting the idea of single-mode optical fibre, he travelled the world promoting the concept to other researchers, for he knew that the idea would get nowhere if the Harlow team pursued the idea alone. The idea was greeted with ridicule and hostility by many, but Charles never lost faith. The Japanese were receptive, but in the US it was largely ignored. Fortunately, he stimulated research programs at the Post Office and the Ministry of Defence in the UK. The support of these two organisations at that time cannot be overstated, for as Charles pushed, they pulled, with the consequence that the UK led fibre technology development for some time. They stated that the loss problem was soluble, despite the current evidence against it, and that the required dimensional tolerances were quite reasonable. They predicted that a figure of 20 dB per kilometre would make fibre communication viable, and this then became the target. Charles and his team now focused on finding and measuring samples of low-loss glasses. He had reason to believe that silica held most promise, but measurement presented a formidable challenge. The samples were only 20 centimetres in length, and with the end surface reflection loss being an order of magnitude higher than the bulk loss. So they had to develop remarkably sensitive techniques. One interesting anecdote from this time, when a meticulous member of the team was asked to measure the loss of a very pure sample of fused silica, he returned with a figure of 0 plus or minus 4 dB per kilometre. Now, like you, we all laughed. He couldn't see the joke, but we all laughed because plus 4 dB per kilometre was such an incredibly small figure for that time. and minus 4 dB per kilometre would imply significant gain. So subsequently, we all quoted the plus 4 dB per kilometre figure, never realizing that in time his zero figure will be much nearer the mark. Fortuitously, the new minimum loss wavelength was 0.85 microns. Whilst the early work showed low loss with red helium neon lasers, we now began to see the trend towards longer wavelength operation, and this would continue in the years to come. For nearly 15 years, Charles's vision of single-mode fibre fell by the wayside. The practical problems of such small dimensions were sidestepped by using multimode fibres with larger 50-micron diameter cores. Modal dispersion was minimized by using graded index refractive index profiles. Attempts to reduce the loss towards Charles's 20 dB per kilometre target seemed stalled. Then, in 1970, Corning invented a new process which you'll hear about in the next talk. This was absolutely vital to the success of fibre. The complete component set now had to be invented, and the next decade saw an explosion in developments around fibre technology. Charles earlier had identified the need for a semiconductor laser in the near infrared, with emission characteristics matched to the diameter of a single-mode fibre core. It also needed to be long-lived and to be able to work at room temperatures. The first semiconductor lasers were little more than a sawn slab with cleaved faces at either end. They only operated with low duty cycle pulses and needed 50 amps and liquid nitrogen and had short lives. There was little control of where the light was emitted, so were unsuitable for launching light into small cores. Later lasers were more sophisticated, the light being confined to a narrow guide, and were capable of continuous operation. These developments later led to optical disc players, which use similar lasers to read and write the discs. These are now the world's most successful and prolific lasers, though you may not have heard so much about them. Billions have been produced. Splicing and connectors seemed a big problem initially, especially for single-mode fibre. Solutions were found primarily through achieving incredible dimensional accuracy of the fibre and associated mating components. The fibres are joined by butting the cleaved ends together, and these are then fused together using a tiny electric arc. Demountable connectors, fibre ends were mounted in highly concentric ferrules and polished, and then pairs of these ferrules would then be connected by inserting them into a precision mating tube. The challenge now was to convince people to invest sufficiently to develop the technology. This 1973 demonstration system used a pulsed gallium arsenide Sawn cavity laser feeding a large core multimode fibre. Despite its modest performance, it later formed the basis of the world's first commercial optical fibre transmission system. This was sold to the Dorset police force after lightning knocked out their coax-based communication link. Meanwhile, the final battle with a much more established technology of the microwave waveguide was now being fought. But fibre had properties that made the microwave solution look somewhat ridiculous. Despite major field trials of the microwave system in the late 70s by the British Post Office and Bell Labs, long-haul microwave waveguide was soon confined to history. However, it prepared the way for optical fibre. It planted the idea of a single waveguide carrying large information capacity. Because it posed huge practical problems, it made fibre look easier to implement than it actually was. And lastly, it provided us with waveguide experts such as Charles Kao and George Hockham. By 1975, continuous operation single transverse mode lasers became available, enabling much higher speed systems. Nearly half the staff were now developing the necessary components for a full system field demonstration in cooperation with what's now British Telecom. We had to design and make almost every part of the system. We were no longer playing with delicate components in a clean lab environment, so we soon discovered what was really practical and what did not work, especially as we needed 6 of everything. I mentioned early earlier that the laser's natural property of high coherence was not exploited in early systems. Well, it came back to haunt us. When the full 6 regenerator system was assembled in the lab, it didn't work. We experienced what we later called modal noise. The combination of lossy fibre joints and laser speckle in multimode fibre killed the system. At the time, we managed to make the system work reliably by deliberately degrading the laser's coherence. It was a wake-up call for all of us and marked the beginning of a return to the elegance of Charles Kao's original vision of single-mode fibre. In addition, the understanding we gained of laser coherence also gave us an early start with coherent optical receivers. There were other factors that influenced the return to single-mode fibre. It had become increasingly difficult to predict the bandwidth of concatenated graded index fibres made using different manufacturing processes. And the improved mechanical precision now meant that single-mode fibres could be joined without excessive loss. Furthermore, to everyone's delight, they proved cheaper to make. The people revolution needed an army of people, and many of you in this room today have been part of that great adventure. Inevitably, I could only cover a tiny fraction of what happened, and I've chosen to focus on the STL story. Each of you have your own stories, which I hope you will record for posterity. I'm forever indebted to Charles. I've enjoyed an exciting 4 decades actively involved in the research and development of optical fibre communications, from its birth to the multi-terabit era. And I'm very grateful for this opportunity to thank you publicly. I believe that what the wheel did for transport, optical fibre has now done for communications. The wheel helped open up the world for 2 reasons. It reduced the energy required to transport material, and it enabled it to be moved quickly. In our next presentation by Peter Schultz, you will hear how optical fibre has done the same for the transport of information. Thank you.